Everyone.
Hello.
Good morning.
Hi. Right, welcome to the second online Neuroccino. This meeting is going to be recorded and put online later on our YouTube channel. The rules of the game are that you just join us for your first or for some even the second meeting on a Monday morning to discuss the exciting science of last week. So you can bring a paper, but you don't have to bring a paper. You're also welcome to just join us with your coffee. Other than that, it's gonna last an hour and there are no wrong questions. Chances are if you don't understand it, someone else doesn't understand it. So just feel free to ask us questions. There is people dropping in and out today who already said they will come and go. I'm going to mute that later so you don't have on the recording. And what else do we need to know? Yes, if you want to present a paper, do let me know by either writing the paper in the chat option or sending me an email. We usually have time for 4 to 5 papers, so it's good to know who has a paper. And I know today there is at least 3 papers. So if you want to present, do let me know and share the title so people can actually open the PDF if they want to. Great, there's chats coming in. Fantastic. And when you do present, please share your screen so everyone can see it as well. That's about it for the rules of the Neuroccino. Just a reminder it's Monday morning. This week, we also have a CNS movie on Thursday at 4 p.m. So do join us for that one. All the information is available online. Now, without further ado, we see one. Here we go. Chris, fantastic, just in time. How about you kick us off this morning, Chris?
Sure.
Over to you.
Okay, share screen. Which one is it? This one. Okay, never shared the screen with the. Do you see the paper or yeah? Okay, cool. All right, so today I wanted to present. I chose a preprint paper, so this has not been published nor and it was not reviewed. So everything in the paper will probably be many things will probably be modified. First, probably the conclusions will be tempered down by the reviewers for sure. But yeah, so it's a paper from Alfred Anwander from the Max Planck Institute in Leipzig, and they want to show that calculating the axon diameter with diffusion MRI is not feasible. So usually I'm not a big fan of paper showing that there is a problem, but they don't give a much solution for it. But it's a preprint, and it can also prevent us from trying the same thing as what they describe as unfeasible. So they simulate basically the best conditions for calculating the diameter of the axons with the diffusion MRI, and they take it's the connectome machines. I think the connectome sequences. They take the best parameters. So I'm not a big expert in diffusion MRI parameters, but they explain first that the diameter of the biggest axons we can find in the human brain are comparable to the limit of the best MRIs we have for now. So even if we manage to calculate it, we would only find the biggest diameters. And they also show that there is a huge signal to noise ratio, and that it will be it would technically be impossible to differentiate the signal we want to calculate the diameter from the noise. Even with the best parameters, they even try to compare to Postmortem parameters. And even in Postmortem, so in Postmortem, the conditions are more ideal even, and it's still impossible to calculate. And they show that the different methods showed. So they explain that there is a trend now to try to calculate this diameter. And so they show the sensitivity is not good enough, not near the sensitivity we would need to actually calculate it. They also show that the effective diameter. So it would require more reading to know what's the effective diameter of the technique is, what the technique is used for. And they explain in the end, yeah, I guess the only good point you can make from this paper about the diameter is they say that we cannot have the intra axon information. But they say that maybe with these techniques, we would have more information about the extra axon environment. And that might be the only good take of these techniques. And yeah, but again, it's a preprint, so it might change. And they're also very like, it's not possible, it won't work. So I think a good take of this paper would be to not try these exact methods. Maybe in the future there will be other methods that would be more accurate. But if you see a paper about axon diameter, I guess you can have some doubts about the results. So yeah. If you have questions, this paper is a bit meaty because there's a lot of equation stuff. So these I couldn't understand.
Thank you, Chris. Are there any questions?
Can I ask? Did they compare the different? Did they compare? Sorry, can you hear me? Did they compare different scanners, or only based on the best one that they can have?
So they did not even use images, I believe. They just compared the calculations with the best parameters. So they have it at the beginning, but yeah, they compared they simulated the calculation with the best MRI parameters we could find nowadays. And I think in the Max Planck Institute there, they have an insane diffusion MRI machine. And yeah, they use the best possible, and even in Postmortem, but they didn't use actual images, I think, because they say there is no point, because even with the best conditions, without adding all the noise we have with the machines, the acquisition, the pre-processing and all, they already cannot find a reasonable measure of the axonal diameter.
Okay, thanks.
Chris,
yeah,
thanks for presenting the paper. Really interesting to see that. I just quickly checked it. I mean, they referred to the Excalibur model of Asaf. Do you know if they actually included that? Because that would really bother me if I would be ASAF and see that my method isn't working theoretically?
Yeah, so I don't know. So I know that they talk about they refer to that method. I don't know if they discussed with Asaf or not. Yeah, I just I don't know how it will go. I mean, also even to publish it, they might have to change a bit their conclusions, maybe soften them a little bit. Yeah, I don't know. I don't know if there is a communication between the teams. I hope there is no conflict of interest. Of course, I mean this is still a preprint, so this is these things we can expect, I guess. But I mean, yeah.
Yeah, I mean, if their results indicate that the model just isn't fitting when it comes to real histological data, then that's quite important.
Yeah.
To know.
Yeah. Yeah. Essentially, that's what they say. They say that this method cannot be used on the scanners we have nowadays, and they even say that even with much more power with the MRIs, it still won't be feasible, because also the results are biased with the biggest axons. So even the distribution, we cannot even simulate estimate the distribution of axonal diameter. So that's pretty bad if it's true. Yep.
Yeah, I just wanted to make a comment. So go ahead, Patrick.
Sorry, Mish. When you say it's not possible to estimate, did they check like to what extent we're actually off the real values? Or?
Yeah, so I don't remember exactly the real the exact numbers, but yeah, from what they show, it's like completely off. And yeah, in the conclusion, they explain that they even didn't consider many other sources of noise and errors that will decrease the accuracy of this calculation. So yeah, it seems pretty bad. But again, it's preprints, so I guess we'll see when it's published.
So I just wanted to make a comment. So I didn't see that before, and it kind of sucked because I kind of managed to start programming the axonal diameter to run it as a routine here. But essentially, they demonstrate mathematically that it doesn't work, but this really clash with the original paper from Yannick Fessav that shows that empirically, when you compare the axonal diameter derived in the brain of mice, you have a match between the estimation and the true measure of the axonal diameter.
Yeah, they also talk about that. Or they don't seem to be convinced with that either. So yeah. In the paper, they say that it doesn't match that well, actually. So,
and there is another paper from Yannick Fessav showing that there is a relationship between speed of conduction derived from EEG between the left and the right hemisphere and the axonal diameter in the corpus callosum.
Oh yeah, they don't talk about EEG, so maybe there's another way.
So it's definitely going to be fight between the theory and the empirical evidence, and well, I look forward to see how this goes.
Yeah, I think there will be a lot of debate about this paper.
Great. If there are no other questions that I can see, no, we can move on to the next paper. So at the moment, I'm aware of 2 more papers. And with that, I give over to Leah. I think you had a paper, right?
Yes. Can you? Okay. Can you see my screen? Bigger. Okay, so this is a paper. Okay, perfect. This is a paper about sorry, I have problem with the volume. Oh, it's not okay. Cool. Okay, try to speak. Okay, sorry. I have a volume issue. Okay, perfect. So in this paper, we have two methods. We have MRI, of course, structural MRI, T1, FLAIR, and also DTI. And they also have echocardiogram, 2D echocardiogram to quantify the cardiac output, like of the heart. And they compare these two different methodologies. And in the subject groups, there are healthy controls with the age above 16 years old, and MCI patients with mild cognitive impairment. And they are split in two groups early. Maybe I can show you this diagram. They can split in two groups, early MCI and MCI. So this is a big population, 326. In a third analysis, they used these data sets, and then they repeat the analysis, excluding some art problems. So the scope of this paper was to see if there was a coupling and a correlation between the volume, heart rate, and the DTI and structural measures, in particular about cortical thickness in T1 images, flare hyperintensities, and DTI measures as FA, MD, RD, and AD, axial diffusivity. And they actually found some interesting correlations. I can show you when they coupled the group, like label the condition, the diagnosis with the gray matter total volume, and also dividing the brain in the different lobes. They found a correlation of in particular in healthy controls, you have a positive correlation. So more is the flux, the echocardiogram measure, and higher was the volume, and also cortical thickness measures. And it is also in the frontal lobe, especially in the frontal lobe, occipital lobe. And they have these findings evaluating healthy controls. In MCI, that seems that there is a different correlation. So in a different relations, this is why the paper is titled that low cardiac output is associated with neurodegeneration, because you have like a thicker cortical thickness measures, but not in MCI. So this seems that in when you have the diagnosis of MCI, something is changing in the correlation of the cardiac output and structural measures. And they also find these correlations, so in volume, cortical thickness, and also in DTI using a TBSS approach. So the cardiac output was correlated with the mean diffusivity, and especially here in the frontal lobe or towards the temporal occipital lobe. And yes, I found this paper like interesting because they based on the hypothesis that they were supposed to find some correlations because in previous paper they found a positive correlation of cardiac output and the size of the brain. And also there are in dementia, there are a lot of paper going on about arterial speed labeling, blood flow measures. So in this paper, they try to merge two different methodologies, and they actually see an agreement. The agreement was not straightforward if you correlate cardiac output with MRI measures, but when you couple with so there is an interaction with the diagnosis. So you have a different trend, a different correlation in healthy controls than MCI. And yeah, it was the paper.
Okay, thank you, Leah.
Can you hear me in some way? Okay.
Yes. Any questions? Can you guys hear me? My audio's all messed up. Okay,
Yeah.
so I can't hear myself anymore. Okay, any questions? No, I can't see any raised hands. Okay, great. Let's move on to the next paper in that case. Michel, I think you have a paper as well. So over to you.
Stop sharing.
Hey, so mine's going to be pretty quick. I've seen this coming up in Nature Neuroscience. It was not last week, but it was like a few months ago. And you know how like science is moving like progressively, is opening progressively to negative findings, where you want to publish a paper saying like, well, no, there is no relationship between this and this. Now the problem is like with standard statistics that we use every day, t-test, ANOVA, linear regression, when we find something significant, we can like, oh, like that's because it's above the odds that we find the relationship between those two things. And we can report it as significant P0.05, for example. But to prove that something does not exist is not having a significant result. And that's essentially what the title means here, which is the evidence of absence, which would be showing a negative result, is not the same as the absence of evidence, which is showing that something is not significant. And so the p-value and the t-test or the ANOVA or the linear regression do not allow us to demonstrate the absence of evidence significantly. But the Bayesian statistics and the Bayesian factor can. So if you run statistics with Bayesian analysis, you don't end up with a p-value, you end up with a Bayes factor. If it's above 3, it's a medium evidence. If it is above 10, it's a strong evidence that you have an effect. If it's between 1.5 and 3, then you don't know, like when you have something not significant with your p-value. But if it's below 1.5, if I remember well, it means that you have the evidence of absence of effect. And then you can demonstrate and report statistically a negative finding. So this is the original papers that have been written by Christian Kaiser. It's a review article in Nature Neuroscience, where essentially he revisits the classical p-values, the relationship between the effect size and the sample size. And you see here that for an effect size of 0.5, which would be the equivalent of a Cohen-D of 0.2, if I remember well, you see like the green means how often you report something significant. The red is how often you miss reporting something significant. And you see, like, missing reporting something significant here doesn't mean there is no effect, because here we do know there is an effect. So this red part here, where you'll be tempted to say, well, I have a negative finding and everybody who published about the relationship between this and that before was wrong. Well, you can see here, this represents like how often you'll be wrong saying that they were wrong. This is not the case with a Bayesian analysis. So I'm not going to get into detail with that, but essentially what you need to know is you can use it, and you can use it very easily with free software such as JASP. You can download it. JASP has been very smartly designed, so you have the standard frequency statistic on one hand, and really in mirror they give you the Bayesian option, which is equivalent of the standard statistics you're doing, except that you'll have a Bayesian factor, and this will help you to actually move on from one framework to the other, testing the same question with statistics, just translating the standard statistics that you know to the Bayesian framework, and be able to report negative findings. JASP is great. I've been using it like a little bit. It's fun, but you need to know and be careful that it doesn't deal very well with very large matrices. If you have very large matrices, I'm afraid you'll have to do it in Python or in a different distribution. But if you look at small matrices, standard, neuropsychology or things like that, then it is a tool that's really going to help you move on and be able to report your negative findings. That's it. Any question? Yeah.
So how does it work? Well, I mean, if you have, for example, a lot of noise, and you're trying to find a relationship between two things, and you have the Bayesian statistics that say, well, there is nothing there.
Mm-hmm.
But it doesn't say that if you remove a lot of the noise, or something, it doesn't mean that you will never find anything, does it?
This will require to be modeled, and it's very, very interesting to explore the relationship between the bias factor and noise. But most likely, the noise gonna push the result in your favor, being significant, and against your favor, which is not being significant. And this is gonna narrow it down to a Bayesian factor, which is between 1.5 and 3, leading you to the absence of evidence. Took me a minute. But if you have less noise and it's systematically a no, there is no relationship, then it's going to bring you to the evidence of absence, which will be below 1.5. If I remember, below 1. Got to be checked. It's below 1, I think. It's below 1. Yeah, sorry about that.
Okay.
Any other questions? So, well, in that case, remember that evidence of absence and absence of evidence is not the same thing, and you can actually solve the problem by using JASP or coding stuff in Python, because like all the Bayesian framework is available in Python, and then citing this great review to back up your rationale.
Best advertisement for this paper, Python and JASP.
I have no conflict of interest.
Great, thank you very much. So I think this is it in terms of the papers. Before you go, I'd like to quickly run the poll with you to collect our stats. So I'm just going to launch it now and give you a minute or two to fill it in. Can you all see the poll up on your screen? Fantastic. Just going to wait for you to answer. Lovely, that is working. That's pretty stable now, so I think this is everyone. So let me share the results with you. Here we go. So the majority is in Europe, as was to be expected from knowing pretty much everyone attending today. In terms of background, we have psychology, a lot of neuroscience, neuroimaging, physics, and biomedical engineering. Degrees, big range from MSc, Masters, BSc, and PhD. Need more coffee, I think. Not really here yet. And you all heard about Neuroccino as word of mouth. So that's great. And in the spirit of that, keep sharing the word of mouth about Neuroccino. The more the merrier. Invite people to discuss science with us every Monday morning. And as I said, this week, do join us on Thursday for the CNS movie, The Fifth Dementia. And that is it. Have a lovely week, everyone. See you next Monday.
Thank you.
Thanks. Bye.
Bye.